Welcome to a video on section 3.2, the derivative as a function. Last section 3.1 we focused on the derivative at a specific point. You may recall that the slope of the tangent line to a function at a particular point A, we also call the derivative, and our definition for it is on the right. F prime of A, or the derivative at A, is found by the limit as h goes to 0 of f of a plus h minus f of a over h. So let's take an example of that and look at the equation of the line. So this example is, given that f of x is square root x plus 1, find f prime 8 and write the equation of the line at x equals 8. So this should be a little bit of a review from the previous section. Let's go through it. Okay, f prime of 8 will be equal to the limit as h goes to 0 of f of 8 plus h minus f of 8 over h. Okay, let's plug in for the numerator. If we put 8 plus h into the function for x, we get square root 8 plus h plus 1. And then let's evaluate f of 8. Let's do that in our head. If we plug in 8 for x, we get 8 plus 1 is 9, and the square root of 9 is 3. So I'm going to put minus 3 over h. You might also notice that the contents inside the square root simplify to just h plus 9. So let's take care of that as well. Now you might get tired of writing the limit h goes to 0 every time. You might just want to play with the algebraic expression. I won't mind that at all in your work. And you might find me doing that from time to time. So let's write this as h plus 9 minus 3 over h. So you might remember the trick here is to multiply by the conjugate. So we're going to multiply the numerator and denominator by square root h plus 9. Remember the conjugate is to change where the terms are, so it's minus, we're going to go plus 3 over the same expression. Square root h plus 9 plus 3. All right. If you ever want to try it, you're always welcome to pause the video and try it for yourself. Okay, so if we multiply this out on the numerator, I might do several steps. The first two terms multiplied together will give me h plus 9. The last two multiplied together will give me minus 9. You might notice that that's just going to give me h. On the bottom, I'm not going to multiply that out. I'm just going to write it side by side. Okay. This is something pretty common that happened in the previous section. Once we do this cool move of the conjugate, these h's simplify. We're just left with a 1 in the numerator, and now we can just plug in our 0. As h goes, we're going to do our limit as h goes to 0. If we did it before, we would have had an indeterminate form of 0 over 0, but now we get a value of 1 over, plugging in 0 for h, we're going to get square root of 0 plus 9 is 3, plus 3, 6. So that is the slope of our tangent line at the point x equals 8 on this particular function. We are wanting to write the equation, so we're going to use y minus y1 equals m times x minus x1. We have everything except for the y value. Now going back to the given information, we want x is 8, so if you would just evaluate f of 8, which we already did by the way, you would find that to be 3. So we did that right at the start there. So that just means the output is 3. It goes to the point 8, comma 3. So we get y minus 3 equals m. That's the slope we found to be 1/6 x minus 8. All right, that is a correct solution. If you wanted to solve for y so that it looks like the slope-intercept form, then that could be found by just distributing. You get y is 1/6 x, and then 1/6 times negative 8 would be negative 4/3, and you got to add 3 to that. Ooh, I can see I have a little bit of extra math there, which I really like. So again, 1/6 times negative 8. Let me just do this work right up here at the top. We got 1/6 times negative 8 would be negative 8/6, or negative 4/3. But then I'm also going to be adding 3 to both sides of this equation. So if I take that, if I take negative 4/3 and I add 3, notice that 3 is the same as 9/3. That's the common denominator, so I can get a value of 5/3. So working with my fractions there, that would be my final equation. All right, so now we're going to move on from that. That's a review of last time to what happens when you think of it as a function. So here I have a pretty cool example with just a common function, g of x equals x squared. That's the red function you see graph there. And then what I've done ahead of time, before this video started, is I've evaluated the derivative at points that follow along this function x squared. So in the table at the right, notice these different x values. These are the g of x values, -9, 9, 4, 1, 0. Those are the points on the red function, right? So there's -3, 9, there's -2, 4, there's -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. But as you evaluate g prime of x, and that can be done by, doing the limit as h goes to 0, all that stuff, right? So I eliminated all that work before this video started. These are all of the values of the tangent lines at any one of those points. And what you can kind of notice is this progression, -6, -4, -2, 0, 2, 4, 6, is a linear function. It's just multiples of 2. It turns out that it is its own function, 2x. G prime of x equals 2x, or just multiples of 2. I want to give you a little bit of a look at a graph here so we can dig into this a little bit more. Okay, here is that same graph as a dynamic Desmos application. So what we have here is that original function x squared, and what I'm proposing is what we call derivative function 2x. So I'm going to go back to this point on the left here. Let me just label it -3, 9. Okay, that means -3 squared is 9. If we look at the derivative there, I have a little graphic here. Notice the dashed line is a tangent line right there. And then the derivative value would be, what is the slope of this dashed line? Well, if you examine that slope, it turns out to be -6. So it's kind of hard to visualize there. But notice down here on the derivative function, at x is -3, the value of the derivative is -6, meaning the slope of that tangent line is -6. But as you progress through this, if you go to the next point, let's drag over there. Notice, well, yeah, the slope changes. It's not as steep. Now at x is -2, the function value is 4, but what's the slope of the tangent line? It happens to be -4. So it was -6, now it's -4. And as we progress, you can go to see to this next point, it's not as steep, it's less negative. And finally, when we get to x is 0, the tangent line is completely horizontal. So the derivative value is even 0. That's why it goes to the origin. By the time we go to this next value, we can see this derivative is finally positive. It's actually a positive 2. And moving on, the derivative becomes a positive 4 and a positive 6. So you can see as the tangent line goes from negative to positive, the derivative goes from being below the x-axis to above the x-axis. Great. So let's examine this just a little bit further. The derivative function, here's your definition. Let fx be a function. The derivative function denoted by f prime of x. So we're not worried about, sorry for moving the screen around a little bit there. We're not worried about defining it at a point, but rather as a function. So all we'll do with our definition is just change it to f prime of x and not evaluate it at any particular a. So you might notice the formula up here in the box looks the same, but rather than a, we're leaving it as x. Let's do that with the one that we just made a picture of on the graph. Let's consider f of x is x squared. Let's find our first derivative function, f prime of x. So it's going to be equal to the limit as h goes to 0 of, well, here's the definition over here. I don't want to rewrite the whole thing. F of x plus h. We're going to put x plus h into the function here, right? So it's going to be x plus h squared minus just f of x, just the regular function by itself. That's just x squared over h. So we need to find this limit. Now you might notice here it looks a little funny because we have both h and x, but it will work out perfectly. So what we'll do is we will distribute the x plus h. Now don't forget, when you figure out x plus h squared, you need to go through all of the work of doing all of the I don't know what happened there, all of the distribution, all right? But I'm just going to cut to the chase. You should get x squared plus 2hx plus h squared, and then you still have minus x squared over h. Didn't write my limit, but that's part of the problem. All right, now notice that x squared, take away x squared is nothing, and on the numerator and denominator of what's left, they all have a factor of h. So I will use the factoring technique to factor a h out from the numerator. From the first term, if you factor a h out from 2hx, you get 2x. If you factor a h out from a squared, you still have an h. And then we have a nice simplification there. No longer indeterminate, so we can just plug in our 0. We get 2x plus, no, remember, h is going to 0, not x, plus 0, because h is 0. or just 2x. So in summary, f prime of x, or the derivative as a function, is 2x. Now, you might think, well, who cares? What do I do with that? Well, the cool part is, once you have this derivative function, you can find the derivative value at any point. You don't have to redo the problem again and again and again, because this is a formula that gives you everything. For example, if you wanted f prime of 8, you might be like, I got to go back and do this whole limit thing again. Not so. If you have a derivative function, you can be like, oh, all I know is f prime of x is 2x. I just plug in my 8, and I know that it's 16. If I wanted f prime of -3, that's nothing more than 2 times -3 or -6. So it might be a lot of work initially to find this derivative function, but once you have it, then you have all of the values pretty quickly with just evaluation. Okay, this box shows you some other notation that we'll use for derivatives, and there's a bunch. All right, so on the left there, these are ways that we can write the function, like f of x or y equals. And so those are the two main options. Our derivative function, we've been using f prime of x. So one way to write what we just did, as you saw me do in the box up there, f prime of x is 2x. You also, if you were given y equals x squared rather than f of x, you would just write y prime equals 2x, which is another way of saying the same thing. And one last option is to write dy over dx equals 2x. Now this seems a little bit kind of cool, but what it's really saying, if you think about dy over dx, the d comes from the Greek letter delta. You might remember that delta meaning change. You might remember change in y over change in x really being the slope formula. That's your rise over your run. The d is the lowercase delta, and so it still means like change in y over change in x equals 2x. That's another way to write the same thing. And then derivative at a point notation is over here. The one we'll predominantly be using is the one at the top here. If f of x is x squared, f prime of 4, and so on. If this is another alternative notation if you're given it the function in terms of y rather than in terms of the function expression, like f of x or g of x. And then one last thing here at the bottom you can do, and this we will be doing quite a bit, is if I just have an expression, if it's not written as a function, I can just write dy dx of x squared equals 2x. So get ready for all of that. All right, some more examples. Using the definition of a derivative, use the definition to find f prime of x for each. I'm going to try the first one here, and then I'm going to have you tackle a few of those with a video pause and get back with the answer in a second. So the first one, if we want the limit as h goes to 0, and remember our formula is f of x plus h, so we're going to replace x with x plus h. So we're going to have 2, I didn't really need that parenthesis, but anyway, 2 minus 3 times x plus h. Go ahead and close it out. Minus just f of x, that's just the function itself. 2 minus 3x. In that case, I did need the parentheses over h. So we've got a little bit of calculus and a lot of algebra here. So being very careful to distribute and take care of all the terms. So we have 2, and then we have distributed into -3 minus 3x minus 3h. And then don't forget to distribute this negative minus 2 minus a negative 3x is plus 3x over h. You might notice that 2, take away 2, cancels out. And then negative 3x plus 3x cancels out. I forgot to write my limit, but let me write that in. And all we're left with is the limit as h goes to 0 of negative 3h over h. And then the h is simplified, and we're literally left with the limit as h goes to 0 of negative 3. It's just a constant function. The answer is just negative 3. And that might make sense because if you think back to this original function, it was a line. It's not in the traditional form, but if it were in the traditional form like y equals mx, it would look like plus b. It would look like y equals negative 3x plus 2. And so you could think about it, oh, that's just a line with slope negative 3, and that's why the derivative is always negative 3. Lines have a constant derivative. Okay, pause the video, try the other two, and then I'll show the solutions. Okay, now that you've given it a shot, I've updated the slide a little bit, or updated the notes a little bit. So if you still haven't finished, try looking at what I have here, pausing it, and finishing from there. Notice the one on the right, on number 3. You need to think of these denominators as a whole factor, x plus h minus 2 and x minus 2. So you'll have to multiply by both of those to find that common denominator. So once again, if you still haven't finished, put a pause on it, and then come back and check the answer. Okay, so I finished those up. There's a lot of algebra steps there. If you need to pause and check those out, please do so. Well, I shouldn't say particularly. Both of those would require quite a few of algebra moves. If you want more on that, you can ask me during office hours. I'd be glad to help out a little bit more. Okay, let's take a look and talk at a new topic we're going to call differentiability, which is pretty much what it sounds like. The ability to differentiate something. So there's a theorem here, and it says if a function is differentiable at a point, it is also continuous at that point. The idea is if you want to find the slope of a tangent line at a particular point, well, you really need to have a point there, and it needs to have some continuity, meaning it has to be going somewhere. So notice I have a beware statement, right? Beware over here. Just because it is continuous does not mean it is differentiable. Okay, so in other words, that statement, that theorem doesn't go the other direction. So and then it goes on to say, given a function, the derivative does not exist at any of the following places. So these are places where we're going to have to watch that there's an issue. So first issue is a sharp corner. If you have a sharp corner, imagine you have a sharp corner. The reason that it's not differentiable is because if you put a point there, how many tangent lines you can draw is infinite. Like you could draw one like that, but you could also draw one like that, you could draw one like that. Since it has that sharp corner, it allows you to draw an infinite number of tangent lines, and so that doesn't seem to make any sense. You're like, I can't do that. So look out for a sharp corner, no derivative there. Add an asymptote. So if you look here at where x equals 3, that's a problem. X at 3, there's really no graph. It goes infinitely up and infinitely down. Since there's no graph, it's not continuous, there's no derivative there. At a point of discontinuity, there's also no derivative because even though it does have an evaluation point, we're up here where the closed end dot is, we don't have a slope of a tangent line because of this discontinuity here. It kind of jumps, and so it doesn't tell you where it's going. The last one is if we have a vertical tangent line. So if there's a point on the graph, or if you drew a tangent line it's completely vertical, that's because vertical lines have an undefined slope and undefined slope. And the reason it's undefined is because you're dividing by 0. If you do think of your rise over run, it's all rise, right? It's straight up and down, but no run. You're dividing by 0, and that is undefined, so it doesn't have a derivative there. So those are your 4 issues: sharp corner, asymptote, point of discontinuity, like a jump discontinuity, for an example, or a vertical tangent. All right, so here are some examples to think about. This first one says, well, the directions are example functions for each of the cases above, and so that's what we're going to be talking about. The first one is what we call a cusp, or this is known as that sharp corner. So the function that I provided here is the cube root of x squared, which can be written in either of these two formats, right? Cube root of x squared, or as rational exponents, 2/3 power 2 root 3. And so that's that sharp corner that you can see right there. No derivative. All right. So if someone asks you what is f, if this is fx, what is f prime of 0? You would say is undefined, and it does not have a derivative. Here as well, there is another sharp corner. So this is a cusp because it's kind of curving and coming back up. We'll call it a sharp corner if it's a line going to another line. The example here is the absolute value of x, and so f prime of 0 also undefined there. Examples for case 1. Let's take a look at case 2. If you have an asymptote, the most common function, g of x, is 1 over x, and you can see that infinite discontinuity there. So again, g prime of 0 is undefined. You can find the derivative anywhere else but 0. Like if I put any point, like if I put a point right there, sure, I can draw a derivative, a tangent line, and so it's doable, but not at 0. Number 3, point of discontinuity. So here we have a piecewise function as a linear, and it jumps to a quadratic. And so add x equals -2, you have that point of discontinuity. So in this case, we would say h prime, did I put my prime on these other ones? Yeah, I did. H prime of -2 is undefined, but it seems to have a derivative anywhere else. And number 4, at a point with a vertical tangent line, I've provided cube root of x, or x to the 1/3. So right here at 0, there appears to be sort of a vertical tangent line. So you would say I prime of 0 is undefined. Now what's cool about this is if you actually go through all the steps for finding the derivative function like we've done in this lecture, you would find that it's undefined algebraically or numerically by looking at that derivative as a function. So here is a graph for you. So this is a piecewise graph, and I'm asking you to sketch the derivative function. Well, how am I going to do that? Just think about it as pieces. Like here, on on the very left side of this graph, it's just a constant function. It's just flat. Well, what is, if I put any point on this, let me just put a bunch of points on this part of it right there. And you drew tangent lines. Wouldn't those tangent lines just be perfectly horizontal? So what is the slope of the tangent line anywhere here? And you might realize, oh, it's flat, so it's 0. So anywhere up to -6, right, that's where it kind of jumps, we have a slope of 0. So from here to here, we say f prime, I guess I'm going to call it f prime of x is nothing, is 0, tangent line 0. So on the graph up through -6, I'm just going to graph a line up through -6. Now since this is a jump, I'm going to put an open dot because I don't have a derivative at these jumps. Alright, now if I look at the blue part and I look at that, it seems to have a constant rate of change, and I can probably just count the slope. Notice if I go down 1, 2, 3, and then 1, 2, 3, 4, it's going down 3 and over 4. That's a negative slope. I would say, oh, okay, here m is -3/4, and so that's from -6 up to x value of 4. We're going to stay at -3/4. So -6 up to 4 over here, I'm going to graph -3/4. Now this is -1 here, so -3/4 is somewhere in here. So it's going to be, it's not that's an open dot, right all the way to here, open dot. All right, and lastly, it jumps to this other graph. What's its slope? It looks like it goes a rise of 2 and a run of 1, 2, 3, 4, 5. So the slope seems to be 2/5 in that particular location, positive 2/5, and positive 2/5 would just be above the x-axis a little bit. And so from here, let's say that's a value of 2/5, about right there. Onwards, it's going to just stay there. So our derivative function is just going to be straight lines showing those different values. All right, now when it's a curve, it gets a little more interesting. This one says, given that f of x is 1/2 x squared plus 2x, draw a graph for fx and f prime x. Now I already did the first part. I already graphed fx on the graph. You can see it there. We're just going to graph f prime of x. And the way we're going to do it is we're going to fill in this table. But we're going to get this points to fill in by first finding what we did above in the class, which is first finding what is f prime of x. So I want you to pause the video and take a moment to try f prime of x using that definition, that limit definition. The limit as h goes to 0 of f of x plus h. You're going to have to be putting x plus h in here and here. Let me show you what that would look like. We have 1/2 x plus h squared plus 2x plus h. That's quite a mouthful there. And then don't forget minus just good old f of x, which is 1/2 x squared plus 2x all over h. That'll take you a bit. As you can see, I don't have room in the margins here. You might want to grab a piece of paper and see what you come up with and come back and we'll continue this. Okay, a lot of work later, way later, right after you did a whole bunch of distributing and simplifying and some more simplifying and some more simplifying, you should have gotten that f prime of x just comes down to be x plus 2. It turns out to be quite a beautiful simplification. All right, x plus 2. And now that we have that function, we can just plug in the values. So filling in the table. When x is -5, you're just going to be plugging that into the function over here on the right. You just think -5 plus 2, -3, -4 plus 2, -2, -3 plus 2, -1, -2 plus 2, 0, -1 plus 2, 1. And maybe you see that pattern. 2, 3, and do I have a little more space here? Oh, that's my last one. All right, now what I can do with those is I can graph all of those on the graph at the right to compare. So the first one, we're thinking of these as ordered pairs, right? -5, -5, -3. So that's back 5 and down 3. 1, 2, 3, be right there. Next one, -4, -2, back 4 and down 2. And then keep going, back 3, down 1, and -2, 0, -1, 1. 0, 2, and 1, 3, and you can see, oh wow, it just happens to be a linear function. And not only that, you probably already noticed this, but if you haven't, you might want to notice this now. If you think back to what we had claimed was the derivative function here, it was just a line. Y-intercept 2, yep. Slope invisible 1 in there. So you can see that is a line with slope 1, y-intercept 2. All right. Approach number 2, find the derivative function. Well, we already did that, so we don't want to just harp on that anymore. All right, let's go on. Working more with continuity and differentiability. So this, you can see in this function here, we have like a curvy piece. It's in green, and then it changes to purple. It's all one function, but I'm using the colors to kind of demonstrate where it jumps from one to the other. The curvy piece is the part of the function that's 2 square root x when x is between 0 and 1, and then it jumps to a linear function 3x minus 1 when x is greater than 1. So what the question is it continuous at x equals 1? Is it differentiable? Justify. So let's answer the questions kind of one at a time. Is it continuous? Well, it's continuous if you can draw it without picking up your pencil. And so as we're coming in from the left, right, where does it go to? And the important piece is when x is at a value of 1. That's what we want to consider. So we're going to look at this piece. We're going to plug in 1 into the top part. 2 times the square root of 1. That's just going to be 2. And then we're going to plug 1 into the bottom part. 3 times 1 minus 1. And that also is 2. So are those equal? Yes. So yes, continuous, meaning there's no jump there. It jumps from one, it goes from one equation to the other, or one part of the equation to the other, but without jumping. So is it differentiable? Well, you think back to those 4 things before. Does it have any of those? And the answer is no. And maybe you can think of why. It has a sharp corner. It's not completely smooth there. All right, let's go ahead, and that's just visual. I didn't prove that. We're going to work on proving that a little bit more later. And the way you can prove it, by the way, is to find those derivative functions. So let's take a look at this example here. So on this one, I'm going to actually do all of the proving and show you what I mean. It is possible to go from a curve to a line, but still be differentiable and not have that sharp corner. In other words, it is possible. Let me just draw something here to have, like, maybe I'm curving along right here, but then at this one point right here, I transition to a line, but when you zoom in, whatever slope I kind of got to at this point, it just kind of continues it. In other words, it was curving, but now it's straight. But at this transition point, I know I didn't do a perfect drawing, there is a smooth transition from one derivative to the other. So what we're asked to do in this problem, this is our last problem, is if k of x is a piecewise function. Let's say it's linear, a of x plus b when x is less than 3, but then it changes to a quadratic x squared when x is greater than or equal to negative 3. Find a and b so that it's both continuous and differentiable. Let's do the continuous first. To be continuous, we want the left and the right to be the same. So maybe put that in the notes here. All right, continuous. We want ax plus b to be equal to, that's the left-hand side, x squared. When? At the transition point, when x is 3. Oh, well, let's just go ahead and plug that in. We'll plug in 3 for x here. We get 3a plus b. And then we'll put 3 for x here is 9. And so we'll come back to that. But for now, we want 3a plus b to be 9. Great. Okay. That didn't get me a and b, but it did give me a relationship. Let's move on. Let's talk about the differentiable piece. For the differentiable piece, let's write what we want here. I didn't write it down in the previous example, but now let's write it down. We want the left and the right to be equal, but we want that derivative to be equal. We want the derivatives of left and right to match. So let's just show that. Let's take a look at the left side. Ax plus b. Now that's just a line. Now we could go through the whole limit approach. Limit as h goes to 0 and all of that, and it would be a way to do it. But I'm going to just jump. And like if we think about a line, what do we know about a line? It always has the same slope everywhere. So the slope here is just going to be a. So I can conclude that the derivative, I'm going to write it in this way, the derivative of of ax plus b is just a. And that's the slope of the line. The other one, I could write it down, but let's go ahead and do the work for the other one. I want to also find the derivative of the right-hand side, x squared, because what I'm trying to do is get those to match. I want it to be a smooth transition. Let's go ahead and go through the traditional walk. Limit as h goes to 0 of f of x plus h minus f of x, just the regular function, over h. Now that might look real familiar, and I don't want to make you dizzy, but we can scroll up to the top and grab our answer from before. Okay, so here I am scrolled back up. You might remember we had done this derivative function already, and so we know that the answer is 2x. I'm not going to redo all of this limit since we already did it, but just know that our answer is 2x. So let's bring that back down here to the bottom. Yep, you're getting a little bit dizzy, but we're almost there. All right, and there we go. All right, so we know that sometime later the answer is 2x. Well, what do we want? We want the derivative on the left and the derivative on the right to match. That's really what we want. So we want a to equal 2x. When? At the transition point. Just like before, when x is equal to 3. So right here, we're going to replace this x with 3, and we get 6. And maybe write that in, x is 3. So we want it to happen at that transition point. Cool, we found out that a equals 6. We actually got the value. Let's pull that back in over here to what we already knew. Now that we know a is 6, let's update this. 3 times 6 plus b. I notice that my 6 and my b look similar, so be careful with that. 3 times 6 is 18. Plus b, it should be 9. We can reason then that b is negative 9. So we figured out a value for a and a value for b, and that just means that if we had a if we had a piecewise function written in the form, and I need to scroll up just a bit so you can see it, ax plus b and x squared, we would write it like this. Ax plus b would become 6x plus b, negative 9, and then on the bottom, x squared. And you would want this one when x is less than 3, and this when x is greater than or equal to negative 3, positive 3. What you would find is that those match derivative and continuously. That's all of this video.